In this video, we're going to take a look at some examples using trig substitution with the sine function. In our first example, we want to evaluate the integral of the square root of 25 minus x squared divided by x squared dx. Since this integrand contains an expression of the form 25 minus x squared, which can be rewritten as 5 squared minus x squared, we know that we're going to want to make a trig substitution, and the substitution is going to involve the sine function, since this expression inside the square root is a constant squared minus x squared. In particular, we're going to make the substitution x equals 5 sine of theta. The 5 is chosen because inside the square root we have 5 squared minus x squared. Well, once we have x equals 5 sine theta, we know that dx is going to be 5 times cosine theta, d theta, the derivative of x. We know that the x squared in the denominator is going to be 25 sine squared theta, just the square of x. And the last thing is to deal with the square root of 25 minus x squared. Now we can substitute in 5 sine theta for x, and we get the square root of 25 minus 25 sine squared of theta. Here we can factor out a 25 from that expression, and we're left with 1 minus sine squared of theta. And 1 minus sine squared of theta we know is equal to the cosine squared of theta. And so now this square root is being taken of a perfect square, and so this simplifies to 5 cosine of theta. And now we have all the expressions that we need in order to substitute into our original integral. We see that 5 cosine theta will be substituted in for the square root part in the numerator. We have x squared to be 25 sine squared theta will be substituted in for our x squared in the denominator. And we have dx here, which is 5 cosine theta d theta, and that will be substituted in for dx. So we will make these 3 substitutions to obtain an integral in terms of theta, and then we can evaluate that particular integral in terms of theta. So we start with our original integral, the integral of square root 25 minus x squared over x squared dx, and we make all of the substitutions that we just indicated. So in our numerator, we're going to be left with 5 cosine theta, the value of the square root expression. In the denominator, we're going to have 25 sine squared of theta, the value of x squared. And we always need to remember to multiply by the expression for dx. In this case, we know dx is equal to 5 cosine theta d theta, and that gets tacked on at the end. And so this is our new integral in terms of theta. Now notice we get a little bit of simplification here. For example, all of our constants are actually going to cancel out. We have a 5 in the numerator from the 5 cosine theta. We're going to multiply that by the 5 from the dx term to give us 25, and that will cancel with the 25 that's in the denominator. We also then can multiply the cosines together in the numerator, and we end up with the integral of cosine squared of theta over sine squared of theta d theta. Cosine squared over sine squared is equal to the cotangent squared, so we can go ahead and rewrite it in that way. So this is just the integral of cotangent squared theta d theta. In order to evaluate this integral, recall from pre-calculus that the cotangent squared is equal to cosecant squared minus 1. This is a standard trig identity. In fact, it comes from the standard Pythagorean identity. Sine squared plus cosine squared equals 1. You can simply divide every term in that equation by sine squared, and the cotangent squared equals cosecant squared minus 1 will fall out of that. And so we have the integral of cosecant squared minus 1 here. And this is actually an elementary antiderivative. Hopefully you recall from calculus that the derivative of the cotangent function is equal to negative cosecant squared. And since we have cosecant squared here, without the negative, the antiderivative here would be negative cotangent theta and minus theta plus c. So the first term, cosecant squared, has an antiderivative of negative cotangent, and -1 is a constant, and so the antiderivative is just negative of the variable, which in this case is theta. So at this point, it looks like we have found an antiderivative for our function, and it looks like we've evaluated our integral. But notice that in our original variable, in our original integral, our variable is x. And here, at the end, it is theta. And so the last step of this type of problem, like with any substitution, is to go back to the original variable, in this case, x. And in order to do that, we need to actually use some right triangle trigonometry along with the substitution that we made at the beginning of the problem. So in order to convert this back to an expression in x, we need to relate cotangent of theta and theta back to x. To find theta in terms of x, we simply need to go back to our original substitution, which was x equals 5 sine of theta. We can solve this for theta by first dividing both sides by 5 to get that x over 5 is equal to the sine of theta. And then we can solve for theta from this by taking the inverse sine of both sides. And so theta will be the inverse sine of x over 5, or the arc sine of x over 5. And this expression can be substituted in for theta in the second term of our antiderivative here, and it involves x, and so this gives us half of what we need to convert back to x. We also have to figure out what cotangent of theta is in terms of x. And to do that, we can use a right triangle approach. So we know here that x over 5 is equal to the sine of theta, and we know that sine of theta, when thought of as an angle in a right triangle, is going to be the opposite over the hypotenuse. And so we can form a right triangle and take an opposite side of our angle. Maybe our angle is here. This is theta. The opposite side will be x, and the hypotenuse will be 5. And we could figure out the third side here by using the Pythagorean theorem. And we see that it's going to be the square root of 25 minus x squared. And so once we know all three sides of the triangle, we're able to write down all of the trig functions of that particular angle. And so the cotangent of theta is going to be the adjacent side, which is the square root of 25 minus x squared, divided by the opposite side, which is x. And now that we know the cotangent of theta in terms of x, we can substitute this in to our expression for theta, for cotangent of theta. And now we have everything in terms of x, and so our final antiderivative will be the negative of this expression, so negative square root 25 minus x squared all over x, minus the inverse sine of x over 5, all plus c. And so our original integral evaluates to this function here. If you'd like to try a similar example, pause the video and evaluate the integral of x cubed times the square root of 4 minus x squared dx. Resume the video to see a detailed solution. Since the integral contains the expression square root 4 minus x squared, and 4 is 2 squared, we're going to make the substitution x equals 2 sine of theta. This means that dx will be 2 cosine theta d theta, x cubed will be 8 sine cubed of theta, and the square root of 4 minus x squared will simplify to be 2 cosine of theta by substituting in 2 sine theta for x and squaring it, factoring out a 4, replacing 1 minus sine squared of theta with cosine squared of theta, and then evaluating the square root of that perfect square. When we substitute all of these expressions into the original integral, x cubed becomes 8 sine cubed of theta, the square root expression becomes 2 cosine theta, and dx is 2 cosine theta d theta. We can rearrange this a little bit to get a constant of 32, which we can pull outside the integral. And then we have sine cubed of theta times cosine squared of theta. This is a standard trigonometric integral. We have an odd power of sine here with a sine cubed. And so we're going to isolate a power of sine and then perform a standard substitution. So after we isolate our single power of sine, we have a sine squared remaining, and we need to convert everything to be in terms of cosine. And so that sine squared of theta can be written as 1 minus cosine squared of theta using the standard Pythagorean identity. We then make the appropriate substitution, which is that u is going to equal cosine of theta, and negative du will be sine theta d theta. And this gives us our integral of negative 32, integral of 1 minus u squared, quantity times u squared du. And keep in mind we have that negative out front from the negative du, from the derivative of cosine being negative. And we can distribute the u squared to get an integrand of u squared minus u to the fourth. We integrate each term using the power rule to get u cubed over 3 minus u to the fifth over 5. And finally, we go back to theta by replacing u with cosine theta, giving us an integral of negative 32 times the quantity cosine cubed of theta over 3 minus cosine to the fifth of theta over 5, all plus c. In order to convert back to the variable x, we use a reference triangle approach. So here we have x equals 2 sine theta as our substitution, which tells us that x over 2 is equal to sine theta. So we can form a right triangle where the opposite side is x and the hypotenuse is 2. This gives us an adjacent side of the square root of 4 minus x squared by the Pythagorean theorem. From this right triangle, we see that the cosine of the angle theta will be the square root of 4 minus x squared, which is the adjacent side, divided by the hypotenuse 2. We can then substitute this expression in for cosine of theta into our integral that we found in terms of theta. So we cube and raise that expression to the fifth and substitute it in, and we get a final function of negative 32 times the quantity of 1/3 times the square root of 4 minus x squared over 2, all cubed, minus 1/5 times the quantity square root 4 minus x squared, all over 2, raised to the fifth power, plus our arbitrary constant c.